Hello everyone, welcome to our PBL Level 1 Physics project. When I was in high school, one of my friends was always complaining about seats. And one day in physics class, it was the optics chapter, and teacher came to him and then he asked him, what is the problem with you? And he said, this is too far and I can see from here. And then he measured the distance from his seat to the board. And then he wrote some calculations. He made some calculations on the board. And then he moved back to him. And then he measured the distance that he's supposed to sit. And then he take him from his seat, from the back to the front. And then he's like, you gotta sit right over here. And then when he moved him to that seat, he was surprised because he was able to see the board really clear. And that was so surprising for all of us because we didn't know what he did and we didn't know how he calculated it. He was a physics teacher, but we didn't really know what he did. And today, actually, we're going to talk about what he did. What he did was very simple. He just calculated the distance from his position, initial position, and after that, he calculated the distance where he's supposed to be. And he just used the properties of lenses. Properties of lenses of the focal length of a lens. The problem was his eye because the lens of his eyes wasn't good enough, so it was probably focusing the image in front or farther from the nerve where it's supposed to be. And today we're going to show you how eye works at the beginning, and after that we're going to explain how you can find the focal length of a lens. This is the model of a healthy eye. And over here, when you have a healthy eye, when the lens of your eye is perfect, then all of the images will be focused at this point, and that's where your nerve is. And that nerve is going to transfer the image over here to the brain, and you're going to be able to see everything clear. But if your eye is not healthy, then your focus is not going to be here. Your focus is going to be either in front or in the back. So right now, this is not a healthy eye. This is, as you can see, those lights are focused in front of the nerve. So what are we going to do? What is the problem with this? Basically, this is curving the lights more than it should. So that means this side is a lot more curved than it should be. And how do we fix this problem? Basically, we're going to open the rays a little bit. So when you have a glass that has a curving in, then that's going to open the lights a little bit. Then you're going to be able to focus the lens. You're going to be able to focus the image at the right position again. Or this is basically called nearsighted. And if you have the problem of farsighted, then this image, this lens is going to focus further from the nerve. So again, at the nerve, you're not going to be able to have a clear image. So what are we going to do this time? We need to curve that a little bit more. So we need to bend those lights more so that it can focus at the right point. So for this, we're going to use another device. So in real life, that's called a glasses. And then that is going to be able to focus the image at the right point. Again, right now, we fix a problem, and that person can see clear. So all we need to do is basically putting a lens, depending on the curve over here. If it's more, then it's going to form the image front and front. If it's less, then it's going to form that in the back. So that by using another lens, we can focus that at the right position again. And after that, we're going to show you how you can find the focal length of a lens. So we need to decide what is the difference between this point and this point, so that we're going to know the lens that we should use. So that's going to determine the size of the glasses that we are using. So it's very important that we know how to measure the focal length of a lens. And in our experiment today, we're going to explain how you can find the focal length of a lens. Alright, we found the focal length of a lens, but where do we use those lenses? Why did we find the focal length of a lens? There are a lot of different places that we use lenses. The one that most of us know is basically telescopes. And what do telescopes do? Basically, we are looking at sky and then we are trying to see farther objects closer. And to do this, we are not using just one lens, because one single lens is just changing the focal length. So we are using multiple lenses, and then we are able to make things smaller or larger. So in this case, we are making this object, this light, coming from that, and then we are making this object smaller. Or if you think backwards, and the smaller object is going to be larger. So that's how actually telescopes work, because light rays are coming from here and then they are enlarged. So basically this is one very important use of telescope. And of course right now this is very simple telescope model. In actual modern telescopes, they're not using those two huge lenses. They are using really tiny and multiple layer of lens sets. So not just two. If you increase the number of lens sets and if you do the correct combination, then you can see galaxies with those lenses. And of course, to be able to do this, those small lenses are not going to work for you. You're going to need a lot more bigger lenses than those, and one set of lens is not going to work for you. Again, you're going to need to use multiple sets of lenses to be able to see larger distances. Another place where we use lenses, of course, cameras and camcorders. And over here, of course, they have lenses, and depending on the quality of the lens, they're going to be able to take the picture of long distances or short distances depending on the lens. So right now this is just like eye working the same. So over here, larger objects and far away, they're going to be focused at this point, and then you're going to be able to, that is going to determine the clearness of the image. Of course, cameras are not used with only one single lens. They have zooming lenses in front, and we're going to show you how those zooming lenses are working. Zooming lenses are also using, of course, lenses. And again, this time we're going to have a little bit different couple of lens sets. So right now the zooming lens is basically to focus to longer distances with clear image. So these are a little bit more sensitive. So by changing the distance in between those two, you are able to change the focus of your image a lot better. And these are more sensitive than the actual lens of the camera. To be able to calculate the focal length of a lens, we're going to need following materials. One of them, the first one, is going to be the light source, and this is Pasco's basic optics light source. And in this experiment, we're going to use this light source as our object. We're going to need a lens. This is again Pasco's 200 millimeter convex lens, a screen to be able to locate our image, and an optic bench to be able to place all of those devices. First, we're going to plug in our light source, and then we're going to place our light source, which is our object in this case, to the optic bench. And to be able to do this, you just place that and then push from the top, and it's going to be securely located in the optic bench. Next, we're going to place our screen, and you can put that farther away from our object or our light source. And next, we're going to place our lens in between our screen and our light source. First, we're going to place our lens to 30 centimeters, and then we're going to move this lens 10 centimeters away from the mirror, from our light source. And then we're going to get 5 different data, and we're going to measure where the image is. And the position of the image is going to be seen in the screen. And that's going to be the distance from lens to the screen. After we place our lens to 30 centimeters, we will try to find the image. And basically we will just move the screen. And wherever we see the perfect image, we're going to stop there. And that's where the image is. And right now, this is a clear image. And it is at 86 centimeters, 85.5 centimeters. Our second data point is 40 centimeters. And this 40 centimeters for our object. And our object is again the distance from the light source to the lens. And once we place that lens here, you're going to find the image at 77 centimeters. But again, we need to get the difference because our lens is at 40 centimeters and we find the image at 77 centimeters. So we're going to get the difference, and 77 minus 40, that is 37 centimeters. Next, we're going to place it to, and the object is at 50 centimeters, the image is at 82. So once we place our object to 50 centimeters, our image is at 82 centimeters. So in this case, this is going to be 80 minus 50, so that is 32 centimeters. And the object is at 60 centimeters. The image is at 88.5 centimeters. At 88.5. So once we get the difference, this is going to be 88.5 minus 60. That is 28.5 centimeters. And the last data point, place our lens to 70 centimeters. The image is at 97 centimeters. So once we get the difference, that is 27 centimeters. So now we're done with our data collection. We will just calculate 1 over SO and 1 over SI. And we know our SOs, this is the position of the object, and we know our position of the images, and then we will just calculate those. But before we do this, make sure that we convert all of the centimeters to meters because the equation is according to meters. So we can just move the decimal point 2 times. And we're going to calculate all of our data according to meter system. This is our focal length equation. So 1 over focal length of the lens equals to 1 over SI. Over here, SI means I stands for image and S is the position. So this is the position of the image. Plus 1 over SO over here. O is the object and S again position. So this is position of the object. And in our experiment, object is going to be our light source and image is where we have the screen. And the focal length is going to be what we're going to be finding. And experimentally, to be able to find the focal length experimentally, equation is a little bit different. This is a line equation, straight line equation in math. Y equals mx plus b. Over here, b is the y-intercept, m is the slope, y is the y variable, and x is the x variable. So to be able to make this equation look like this, we're going to need to have 1 over SI on the y-axis, 1 over SO on the x-axis. And when we have this graph, we're going to have a straight line. But the slope of the straight line is going to be approximately -1. So in our equation, y equals 1 over SI, x equals 1 over SO, and m equals -1. So once we place all of them into that equation, our b, which is the y-intercept, is going to be 1 over focal. So the focal length is going to be 1 over b. So to be able to get this graph, what we need is we're going to have SO to SI. What we're going to do is we're going to place objects at different positions, and then we're going to measure where the image is, and then we're going to calculate 1 over SO and 1 over SI values. And once we complete this data table, we're going to plot 1 over SO to 1 over SI graph. And once we have that, we're going to find the b, which is the y-intercept, and then 1 over b will be equal to our focal length. So 1 over 0.4 is 2.5. 1 divided by 0.37, 2.7. 1 divided by 0.5 is 2. 1 divided by 0.32, 3.1. 1 divided by 0.6, 1.6. 1 divided by 0.285, 3.5. And 1 divided by 0.7, 143. And 1 divided by 0.27 is 3.7. Our first data point is we're going to plot our data 1 over SO to 1 over SI. And on the x-axis, we're going to have 1 over SO. And on the y-axis, we're going to have 1 over SI. And our y-intercept is going to be our 1 over focal length. So let's plot our data. So 3.3 to 1.8. So that's our first point. 2.5 to 2.7. Second point, 2 to 3.1. Our next point is from 1.666, which is 1.67. So it's somewhere here, to 3.5. And our final point is 143 to 1.4 is right here, so 1.43 to 3.7. And it's somewhere here. So these are our 5 data points, and we're going to draw the best fit line. And it is something like this. And we need our y-intercept. So our y-intercept is 4.2. And this is equal to 1 over focal length. And from here, our focal length is 1 over 4.2. And this is equal to 1 over 4.2. And this is equal to 0.23, 0.24. And this is equal to 240 millimeters. So that's the focal length of our lens. And of course, it's an experimental value, and the theoretical value should be on the lens itself. And that is 200 millimeters. That is a theoretical one, and that is our
experimental value.
Thank you for watching our PBL Level 1 Physics project. I hope you enjoyed it. See you next time.